Okay, so in this video we're going to talk about 4.10 antiderivatives. So antiderivatives are exactly what they might sound like. They're the opposite of a derivative, so going backward. So for example, if I give you the derivative of x squared is 2x, we already know that. So then the question is, what's the antiderivative of 2x? Well, it's x squared, so it's kind of like it's working backwards is what that is, all right? So the other thing, though, you might notice is that the derivative of, let's say, x squared plus 6 is also 2x. So if I were to work backwards, the antiderivative of 2x could also be x squared plus 6, or x squared plus 7, or 12, or pi, or a constant. So the derivative of x squared plus a constant is 2x, which means the antiderivative of 2x is x squared plus a constant. And we're going to use that c to mean a constant. And this is called a family of antiderivatives, okay? All right, so let's just do a couple of examples. So the first one, the antiderivative of 4x cubed, we're going to use capital F as the notation there, would just be x to the fourth plus a constant, because the derivative of x to the fourth is 4x cubed. Okay, all right, so then the antiderivative of secant squared would be tangent of x, yep, plus c, again, because the derivative of tangent is secant squared. And then the antiderivative of 1 over 1 plus x squared would be arctangent of x plus a constant, again, because the derivative of arctangent is 1 over 1 plus x squared. Okay, all right, so that's the idea. So now we're going to work on the notation. So the notation, there's definitely more than one way you can think about a lot of these, but we're going to use the indefinite integral, to mean the notation here. And so what that is talking about is this integral symbol right here means antiderivative of f of x dx with respect to x. So when we're computing the indefinite integral, you're going to include all antiderivatives, including that plus a constant as well. So the integral of 4x cubed is x to the fourth plus a constant. All right, so then let's do a couple of examples, all right? So what about finding, in this case, the integral of x to the power of something? So I have a formula here. This is called, I'm going to give it a name here for you so you can see it. This is called the power rule for antiderivatives, All right, so this is sort of the opposite of the power rule for derivatives, of course. And so how do you prove that something is an antiderivative in general, all right? So what I'm going to do is, I think this is the answer, right? I'm going to prove this formula. So I'm going to take the derivative of that and show I get the original question. Okay, so how do we do this derivative? Then hopefully I think we can recognize it. Hopefully you can see that p plus 1 is a constant multiple, so it will stay. And then I'm going to bring the power down, and x to the power of p plus 1 minus 1, and then the derivative of a constant is 0. And then you should notice that things cancel, and I end up with x to the power of p, which, of course, worked, right? Because that was the original question. All right, so what that really means then, so like as an example, the integral of, let's say, x cubed dx would just become x to the fourth over 4 plus c. So you add 1 to the power and divide by the new power. All right, and then a couple of other things just to notice here along the way is that constant multiple will still work. So if you have a constant multiple, you can leave it alone, right? Or it can come outside the integral. You can break the integral up across a plus or a minus. That could also probably include a minus there as well. Okay. All right, so let's do a couple of examples there so we can make sure we're comfortable with what's going on here. So same idea, that 4 is a constant multiple here. So when I'm integrating 4x to the fifth, that 4 is a constant multiple. And then I add 1 to the power and divide by the new power. Easy enough, okay, and then minus, and then I can do a 3 is a constant multiple, and then I will add 1 to the power, divide by the new power, plus. That 17 is a constant multiple. I can add 1 to the power, divide by the new power, minus. Now, the antiderivative of 5 is just 5x, and that's pretty simple. That's just because the derivative of 5x is 5. That's sort of all there is to that. Okay, let me move up here a little bit. All right, and then, of course, simplify. So then I had a 2/3 x to the power of 6 minus x cubed plus 17/2 x squared minus 5x plus a constant. All right, so that's that antiderivative. And you can always check your work. So how would you check your work? You would check your work by taking the derivative of this and making sure it is the same as the question. All right, that's how you would check your work. All right, so let's go ahead and do another example. I'm going to zoom in here so I have more space. So the next one, to think about this one, there is no quotient rule for antiderivatives. So I have to break up that fraction. There's no other way. So then this is going to become I've got the integral. I'm going to keep that integral symbol there because I do not yet know the antiderivative. Then I have a 7. Now, x to the power of 18 divided by x to the power of 4 is x to the power of 14. You can subtract those exponents. Minus 15x to the 8 dx. And then I'm going to do the antiderivative. Okay, so then I have a 7x to the power of 15 divided by 15 minus 15x to the power of 9 divided by 9 plus a constant, of course. Ta-da. Right, so now how would we move on? So I'm going to go, actually, let me zoom in past this a little bit. So how would I find the integral of sine of 3x dx? So what I'm going to do is I'm actually going to make a guess. All right, so what am I going to do? And the way I'm going to guess, I think the answer is cosine of 3x. Okay, because I feel like sine and cosine are pretty well related when I'm doing derivatives and antiderivatives. But how would you check your work? So you would take the derivative, right, of what I think the answer is. So let's do that. So the derivative of cosine of 3x is negative sine of 3x times the derivative of the inside. Now that doesn't match what I have. So that means that that was not the right answer. So I'm going to try a different guess. But you might notice how close I really was, right? The only thing that was off between what I got when I did a derivative in the original question was an extra negative and a 3. That's what wasn't here. So in my guess, my new guess, I'm going to try to just get rid of that negative and the 3. And then again, how do you check your work? You take the derivative and see what happens. So that negative 1/3 now is a constant multiple and it can stay. And the derivative of cosine is negative sine of 3x times the derivative of the inside. And then in this case, those things cancels. Like that 3 cancels, that negative canceled. And I got sine of 3x, which works because that was the original question. Good, good, good. So that means, so now I can rewrite this. So now I have the integral of sine of 3x dx is negative 1/3 cosine of 3x plus a constant, because that ended up being, that worked when I checked my answer there. So you might notice a couple of things. So really the main thing I want to notice is just a pattern, so I can use a whole bunch of these moving forward. What I really did is the integral of sine ended up being negative cosine, but I divided by that constant multiple. All right, that's what that really was. I divided by that constant multiple. And then you might notice a few other ones too. So that's sort of the general idea of what's happening here, but then I'll give you kind of a pattern here. So I got a whole bunch of them here for us in our notes. There we go. And this is sort of the pattern. On the left-hand side, I have a bunch of derivatives, but on the right-hand side, there we go, now I can see them all. On the right-hand side, I have a bunch of antiderivatives. Let's see if we can make sense out of some of those. I think we can. So the integral of cosine is sine, because the derivative of sine is cosine, but you just have to divide by that constant multiple again. The derivative of sine is negative cosine, because the derivative of cosine is negative sine. That's why we're doing an antiderivative, and again, just another constant multiple. And then the same thing, the integral of secant squared is tangent, because the derivative of tangent is secant squared, and the integral of cosecant squared is negative cotangent. The integral of secant times tangent would be secant, and the integral of cosecant times cotangent would be negative cosecant. All right, so a few more things to recognize. This isn't necessarily new information, it's just undoing the derivative. All right, so then we just got to practice. Okay, so for this next example right here, I'm going to see if I can highlight some things. The integral of secant squared of 1/2 x. So the 1/2, oh, there we go. The 1/2 is the a in this case. So then the integral of secant squared is still tangent, and you leave the argument the same, but then you have to divide by that constant multiple. All right, which of course just turns into a 2 times tangent of 1/2 x plus a constant. Cool. All right, so then a couple of more. So same idea, let's just keep practicing. What I'm going to do is I'm actually going to remove those formulas from the screen so we can just try to think about it in terms of derivatives. Okay, so let's just think about it just in terms of derivatives and antiderivatives that we already know. So the integral of 4 times cosine of 7x. All right, well, 4 is a constant multiple, it stays. The antiderivative of cosine is sine, because the derivative of sine is cosine. Now the argument stays the same, and you divide by the constant multiple. Ta-da. Let's do another example. Let's throw in another one. So what if I had like the integral of, let's say, secant of 2x times tangent of 2x. Okay, let's do that same one. Okay, so really the same process. The integral of secant tangent is secant, because the derivative of secant is secant tangent, and then divide by the constant multiple. Excellent. Let's do one more. Just one more. All right. So what about the integral of, let's say, sorry, there we go. Negative 2, there we go. Negative 2, let's say cosecant of 3x times cotangent of 3x. Okay, there we go. So that negative 2 is a constant multiple. It can stay. And then the antiderivative of cosecant cotangent is negative cosecant. And then the argument stays the same, and you divide by that constant multiple, which in this case ended up with the negatives canceling. So I got 2/3 cosecant of 3x plus the constant. Ta-da! All right, so that's the idea of those antiderivatives with trig functions and power rules. Now there's a couple of more that I just want to make sure that we are comfortable with. So again, same process, right? I've got some derivatives on the left side and integrals on the right side. So if you see them right next to each other, it should help you make a little bit more sense out of it. So the derivative of e to the something, right, or e to the x, was just e to the x. That extra a here in that derivative came from the chain rule. So now we're thinking about antiderivatives. So the integral of e to the ax is 1 over a e to the ax plus the constant. Again, you're dividing by the constant multiple. Okay, now a couple more. The integral of 1 over x is ln of x, because the derivative of ln is 1 over x. So there's kind of the antiderivative there. Now then a few more for some inverse trig. Now maybe you remember those derivatives over here on the left-hand side for the inverse trig, but maybe you don't. We do need to go back and remember some derivatives of inverse trig. And then this is undoing that, the antiderivative. Okay, that's where that's going to come from. Let's do some practice. So now we see those. There is a lot of remembering some things from derivatives as well. Let's practice. So the antiderivative, or the integral, of e to the negative 8x dx would be e to the negative 8x, but divided by that constant multiple, because the antiderivative of e to the x is still e to the x. Good, 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 good. All right, so let's practice, let me actually do one more. Before I do part B there, let me just throw in one more example really quick. The integral of, let's say, 5 over x dx. Well, that 5 is a constant multiple. And then that would be a 1 over x, and the antiderivative of 1 over x is ln of the absolute value of x. Okay. All right. Let me actually even throw in one more. I know I'm kind of doing it out of order, so I'm going to do one more example. So what if I did the integral of, let's say, 1 over, let me undo that, sorry. Let's say 4 plus x squared dx. Now, you might go back and notice, if you look, it's still up here, this tangent inverse integral. So 1 over a squared plus x squared is 1 over a tangent inverse of x over a. Right, okay? So then you just have to notice the comparison. So in this case, what I have here, let me highlight it, there we go. My 4 is now my a squared. So if that's the case, then my a is actually 2. So then this antiderivative would be 1 over 2 tangent inverse of x over 2, plus the constant, of course. Okay, so now that's a lot of information going on, definitely a lot. But let's do that part B. Okay, so that part B was, oh, sorry about that. There we go. That part B was the integral of 1 over 16x squared plus 1 dx. I'm actually going to try to simplify this a little bit. So this is going to become the integral of 1 over 16 times x squared plus 1 over 16 dx. If you remember, the factoring is really just a fancy word for divide. Okay, so hopefully that makes a little bit of sense so you can see that those two are the same. And then I'm going to simplify even farther. This is now a 1 over 16 on the outside of the integral. And the reason being is because now that 16, that 1 over 16, was a constant multiple. Okay, all right, now I'm going to write something else up one more time so we can see it all on the same screen here. On the previous slide, we had, or on the previous page, excuse me, we had a formula. The formula was the integral of 1 over a squared plus x squared dx is 1 over a tangent inverse of x over a plus a constant. Okay, now we have to compare. This looks a whole lot like that. But I just have to highlight, so my a squared is now 1 over 16, which means my a is 1 over 4, the square root of that. Yeah, you got it, good. All right, so now let's continue on with that. That 1 over 16, this 1 over 16, excuse me, is going to stay. Okay, and then I have to do this integral. And that integral is 1 over a times tangent inverse of x over a. You just have a little bit more complicated of an a. So then I simplify this. I have 1 over 16 times 4 tangent inverse of 4x. That's how you divide fractions, of course. And then that'll become a, probably a 1/4. There we go. 1 over 4, because 4 over 16 is 1/4. Tangent inverse of 4x plus a constant. Whew. Ta-da. Okay, so just the last couple of practice here. There's a ton going on. You definitely want to practice antiderivatives over and over and over again, just like you practice derivatives over and over and over again. But let's do one more. So all of this time we've been doing these antiderivatives with the plus c going on. But let's actually solve for that c. Let's figure out what that really means. So in this case, I'm going to give you, in this problem, I'm giving you a derivative. And I'm giving you a function value. Notice there's no derivative here. So I'm giving a function value, and I'm asking you to find f of x. Okay, so we can do this. So I'm going to undo the derivative. So, well, that's easy. If I'm given the derivative and I'm asked to find the original function, well, that's just an antiderivative. So x cubed over 3 minus 3x squared over 2 plus a constant. I added 1 to the power divided by the new power. Pretty easy. But then I'm going to use what's called an initial value. So what that means is that I'm going to plug in 1 to my original function, and it better be equal to 1/2. Okay, that's what that means. Let's write that out in the correct notation. So f of 1 is 1/2. That just means I'm going to plug in 1 into my function, and it better be equal to 1/2. And then I can solve. So now I have a 1/2 equals. That's a 1/3 minus a 3/2 plus a c. All right, and then I'm going to go ahead and do that arithmetic. So what's 1/3? Oh, no, I said plus. I'm sorry, minus. Thank you. 1/3 minus 3/2 is -7. Sorry, there we go. -7 over 6 plus a constant. And then, of course, I'm going to run out of space. I'm sorry. So then I'm going to have that my constant is whatever 1/2 plus 7 over 6 is, which is 5/3. Okay, so then I have that c. So then what I can actually do is that now I know that c is 5/3, I can replace it. So my actual function now is equal to x cubed over 3 minus 3x squared over 2 plus 5/3. Cool. Ta-da. Okay, let's do one more example. We'll just do the last one here for 4.10. So a mass oscillates up and down on the end of a spring. Find its position function if you know its acceleration. All right, so here's what's different. I'm going to write a few things that hopefully we remember from previous sections. If you're given, let's say, a position function, then its derivative is the velocity. All right, and its second derivative is the acceleration. So now what we're really talking about is working backwards. So I'm given acceleration, and I want to work my way backwards to position. Now, of course, that's antiderivatives. All right, so let's do that. So I know that my acceleration is sine of pi times t. Now I'm going to do the antiderivative. If I do the antiderivative, that's just one antiderivative. That's going to give me velocity. So now I have that my velocity is, let's do the antiderivative. Now the antiderivative of sine is negative cosine. So it's negative cosine of pi times t, but don't forget to divide by that constant multiple. Good, good, good. All right, and then plus the constant, of course, plus the constant. So now I have that. Then you have to solve for that constant. So I'm going to kind of do this in a different color each time. So I know that v of 0 is 3. So now I have a negative 1 over pi cosine of pi times 0 plus the constant. Because I literally just, this means plug 0 into your velocity. So I plugged 0 into my velocity. Nothing too fancy. Now I'm going to simplify that, of course. So now I have a 3 is equal to cosine of 0 is 1. So 3 is equal to negative 1 over pi plus the constant. So my c is going to be 3 plus 1 over pi. So then you can rewrite your velocity. It's negative 1 over pi times cosine of pi t plus 3 plus 1 over pi. So there's my velocity. Okay, so which is really good. I found the velocity. Unfortunately, the question actually asked me to find the the position. Oh, I should scroll down here. Maybe if we can see it. I zoomed out. There we go. There we go. Okay, so if you notice, sorry about that. It said find the position function, and all I have is the velocity. So now we're gonna have to move on. All right. So we gotta keep going. I'm gonna kind of scroll up. There we go. And there's more that I'm gonna need to find. So now I'm gonna do my position. One more antiderivative. If I do the antiderivative of acceleration, I'll get velocity. And then the antiderivative of velocity, I'm going to get position. So let's do the antiderivative. That 1 over pi is a constant multiple. It can stay. And then the antiderivative of cosine is sine. And I leave the inside the same, but don't forget to divide by the constant multiple. Good, good, good. Plus the antiderivative of 3 is just 3t. Plus the antiderivative of 1 over pi is just 1 over pi times t. So anytime you have the antiderivative of a constant, you can just throw in that extra variable there, which is nice. And then, of course, just like last time, we have an initial position right here. S of 0 is equal to 0. Okay, so that just means I'm going to plug in 0. So I have negative 1 over pi squared times sine of pi times 0 plus 3 times 0 plus 1 over pi times 0 plus c. And then I simplify, so I have 0 equals, let's see, sine of 0 is 0. So then that'll become a 0 plus 3 times 0 is 0 and another 0 plus c. Okay, so real boring. I just got c equals 0. That's all right. Sometimes you get c equals a fancy number. Sometimes you get c equals 0. You never know until you try. Every time is slightly different. Okay. Okay, so then I have my position function. So s of t is negative 1. I'm just rewriting it. Okay, s of t is negative 1 over pi squared times sine of pi t plus 3t plus 1 over pi times t plus 0. Now, of course, you don't need to write that plus 0, but you could. Ta-da!